Hi everybody, Mr. Johnson again. This is lecture 7, section 3.5, composition analysis. We are on page 144 of our ebook or 136 of our hard copy textbook. Just want to take a moment to explain what this graph is here at the beginning of this section. This is a mass spec graph. We'll talk more about them later, but what this is coming from is a sample of a compound. In this case, it was hexane, was put into this machine, a mass spec machine, and through some very sophisticated technology, the machine spits out the masses of the different atoms that were in that sample and their relative abundance, which can ultimately be converted to their percent abundance. So it's telling us what the atoms are in that sample and what their, again, percent or relative abundance is. Analytic chemists are often trying to figure out what a substance is, to identify it, to know what its uses are, its properties are. And one way to do that is through a mass spec and figuring out again what the elements are that are in it and their percent abundance. So that's providing a little bit of context for why it is that we are about to learn this type of math problem we're doing, which is to calculate a percent abundance from a known formula. The idea being that if from a mass spec you can get the percent abundance of these atoms in an unknown molecule and could compare those data to the percent abundance in a known molecule, that could be one way to know that that unknown substance is this known molecule. So we're looking now toward the bottom of the same page to the section titled percent composition, and the definition of percent composition is the percent of a compound's mass contributed by each type of atom in the compound. And then it goes on to say a compound's percent composition can be determined theoretically from its formula. And that's what we're about to do, is to use a formula for a compound, which will tell us the types of atoms in it and how many of each type there is, and do a bit of math to figure out what the percent abundance or percent composition of each atom in that compound is. So I'm going to do it a little differently this time. When we solve our first problem together, I'm going to walk you through the sample problem that's already solved for us at the top of this page. I've just flipped my page to 145 of the ebook. Then I'll give you a chance to try a practice problem on your own. That's going to be practice problem 2. I'll recommend you pause it after you try, and then we'll look at my solution together. So the first step to solve a percent abundance or percent composition problem is to calculate the molecule's molar mass. In this case, it's sucrose, C12H22O11. So we see that the first thing to do is to account for that there's 12 carbon atoms in this molecule. Our book has 12 moles of carbon over 1 mole of the molecule. You could also have said 12 carbon atoms per 1 molecule. So we're multiplying 12 by the mass of each carbon atom. Again, our book is only using 1 decimal place for molar masses. I recommend you use 2, so we would have 12.01 in there. So we're multiplying 12 carbon atoms by the molar mass of each carbon atom, which gives us that there's 144 grams of carbon in a mole of this molecule. We do the same thing for hydrogen. We multiply its subscript by its molar mass. Again, we'd use 1.01, and that means that in a mole of this molecule, there'd be 22.20 grams of hydrogen. We were using 1.01. For oxygen, same thing, 11 oxygen atoms times the molar mass, 176 grams per mole. So we add those numbers up to get the molar mass, and we learned how to do that already. But notice that in the work that we're doing this time, we're very explicitly showing and writing out what the mass is of each element in the compound, because we're going to use those 3 numbers below. So then to find the percentage by mass, this, by the way, is mass of each element in the compound, we take the mass that that element contributes to for the total compound. In carbon's case, it's 144, and divide it by the molar mass. And that's 42%. For hydrogen, again, it's the mass that the mole of hydrogen atoms contributes to the overall molecule, divided by the molar mass of the molecule. We get 6.4%, and we do the same thing for oxygen. So it's these 3 values from above that are divided by the molar mass of the molecule that give us the percent composition of each atom or element in that molecule. So I'm going to recommend that you try practice problem 2 on this same page by yourself to find the percent composition of nitrogen, hydrogen, sulfur, and oxygen in ammonium sulfate. And then once you're done, hit play again and compare what you did to my solution. Great, so here's my solution. Again, it's ammonium sulfate, whose percent composition by mass we're finding. I've distributed this 2 into everything within the parentheses. So there's 2 nitrogens, 8 hydrogens, just 1 sulfur, and 4 oxygens, and that's reflected there. I've then taken the number of each atom and multiplied it by its molar mass. That's nitrogen's molar mass. So that would be the number of grams of nitrogen in a mole of ammonium sulfate. 8 hydrogens times its molar mass, 1 sulfur times its molar mass, 4 oxygens times its molar mass. These are the masses of the 4 elements if there were a mole of the compound. I've added them up, and that's the molar mass of the compound. And that really should be grams per mole, but we'll leave it as grams. So then what over here I've done is taken the mass of each element in a mole of the molecule and divided it by the molar mass. So there's nitrogen, hydrogen, sulfur, and oxygen that I've done that for. And then I've rounded them. Of course, I multiply that by 100 for it to be a percentage as opposed to the decimal equivalent. And I've rounded them all to the right number of significant figures. Notice the percent hydrogen has 1 fewer sig fig than do the other 3, because the molar mass of hydrogen in the numerator had just 3 sig figs, and therefore the final answer can only have 3 sig figs as well. If you feel like it'd be helpful to do one more practice problem before we move on to the next type of problem, consider doing either practice problem 1 or practice problem 3. And then remember, the answers to all the problems in our book are in the advantagescience.com website, not the ebook. Under chapter 2, you'll find them. So I've flipped my page to 146 in the ebook or 138 in the textbook, and we're on this section here at the top titled Empirical, Molecular, and Structural Formulas. Before we get into these definitions, I'm going to take us to a web page so we can see a visual representation of these different types of formulas depicted in an image. There's 3 main types of formulas we work with in chemistry, and particularly in organic chemistry, which will actually be our unit ideally after the AP test. The most explicit of those types of formulas is called the structural formula, and a structural formula depicts not only the types of atoms in the molecule and how many of each there are, but how they're arranged 3-dimensionally in space. This is a glucose molecule here. There's a hexagonal portion to the molecule with 5 carbons and an oxygen. And then coming up and down out of the plane are these other atoms, hydrogens and hydroxyl groups. And this is a methoxy group. Don't worry about what those are called. So it's the most explicit because it tells us, again, not only the types of atoms and how many of each there are, but how they're arranged in space, which matters a lot to how that molecule might behave in nature, might function. One step down in explicitness from that is the molecular formula, which just depicts the types of atoms, carbon, hydrogen, and oxygen, and how many of each there are. And that's the type of formula you're most familiar with. Well, even less explicit than that is what's called the empirical formula, which depicts the lowest whole number ratio of each type of atom to one another in that molecule. In this case, it's CH2O. And to go from the molecular formula to the empirical formula in this case, all the subscripts were reduced by 6. If we were to go from the empirical to the molecular, that would require multiplying each of the subscripts by 6, which is something we'll be doing a little bit later when we solve some problems. So again, those are the 3 types of formulas, from most explicit to least explicit. And in a moment, we're going to learn how to, from some data, figure out what the empirical formula is of a substance, and then what its molecular formula is as well. So we see those 3 types of formulas at the top defined. Empirical formula, again, is the simplest integral ratio, or I said whole number ratio of the different types of atoms in the compound. Molecular formula is the actual number of each type of atom in the molecule. And then structural formula also shows how those are arranged in a diagram, what their 3D structure is if it's a 3D molecule. And again, we're going to be learning how to find the empirical and molecular formulas of certain substances. If all we know about a substance is its empirical formula, we may very well not know what it is, because many types of compounds, many compounds in nature have the same empirical formula but different molecular formulas. So too do some molecules have the same molecular formula and different structural formulas, and that makes them actually behave a little bit differently in nature. So ultimately, to know what kind of a molecule we're dealing with and how it's going to behave, we want to know the structural formula. That's not something we're going to learn how to do today. It'll come to us later. So I've scrolled down just a bit on this page, looking at this quick check here, and I invite you to fill in this quick check, to write the molecular formula for each of these compounds and their empirical formulas as well. And then pause and compare your answers to mine in just a moment. So all I did is count atoms, 2 carbons, 4 hydrogens, and 2 oxygens. And what I didn't mention, but I will now, is that in organic chemistry, carbons tend to be listed first in the formula, followed by hydrogens, followed by oxygens. But there's some exceptions to that. If we reduce those into the simplest ratio, divide them all by 2, we get CH2O for the empirical formula. And for this molecule down here, 2 carbons, 2 hydrogens, and 4 oxygens, and when reduced, that's CHO2. All right, so we're now looking at the section titled Determining an Empirical Formula from Percent Composition, and shortly we'll learn how to do that mathematically. A bit ago, I talked with you about how from a mass spec reading, you can figure out what the percent composition by mass of a substance is. And compare that, let's say, to the formula that's known for a compound, and compare those percentages. Well, you could be comparing all day to a variety of formulas. Instead, what can be done is from the percent composition data, like we learned how to calculate a bit ago, you can perform another mathematical operation to figure out what the empirical formula is, to go straight to the empirical formula. And then with one other piece of information, which also comes from a mass spec, if you also know the molar mass of this substance, of this unknown substance, you can figure out what its molecular formula is. So the next little section is going to teach you how to, from percent composition data that either is already given to you or that you've found in a prior problem, to determine the empirical formula, and then with one other piece of information from an empirical formula, you can determine a molecular formula. Before we solve a problem with actual numbers, let's just talk about why we would be doing the steps we're about to do. Let's say that our goal is to find out that the empirical formula of a substance is CH2O, that somehow that's something we'll figure out. Well, if that's the case, if that's the empirical formula, what that means is that there's 1 carbon atom for every 2 hydrogen atoms for every 1 oxygen atom. Or if we scale it up by Avogadro's number, we could say that for every mole of carbon atoms, there's 2 moles of hydrogen atoms and 1 mole of oxygen atoms. There's a mole ratio of 1 to 2 to 1 for carbon, hydrogen, and oxygen. What that means is if we know how many moles, how many actual moles of each atom there is in a compound, which can be arrived at through laboratory procedures, and we figure out what that mole ratio is, what that lowest whole number mole ratio is, that mole ratio becomes the empirical formula. So what we need to get from the math we're about to do is how many moles of each atom there is in a sample to figure out what the mole ratio is, to then translate that to an empirical formula. And then if somehow we know the factor by which an empirical formula needs to be multiplied to get the molecular formula, if we somehow know how many times more atoms overall there is in the molecular form in the empirical formula, or how many times more massive, same thing, the molecular formula is than the empirical formula, then that's what it takes to go from empirical to molecular. So we'll do the same thing again this time. I'll walk you through this sample problem, and I flipped my page. I'm now on 147 of the ebook. And then invite you to try a practice problem on your own, and then you can compare your work and your answers to mine. So we are being asked to determine the empirical formula of a compound that is 48.65% carbon, 8.11% hydrogen, and 43.24% oxygen. Remember, those are by mass. You could also, in a problem like this, just be given the masses of each element as opposed to their percent composition, and you would solve it the same way. If we're given a percent composition, which in this case we are, we just assume we've got 100 grams of the compound. Because if you've got 100 grams of the compound, then each of those percentages by mass become grams. And notice that down here, where the work is shown, 48.65% carbon became 48.65 grams. And so is that the case for hydrogen and oxygen. So as a bit ago you heard me say, we've got to figure out how many moles of each atom we have so that we can ultimately figure out what the lowest whole number mole ratio is. Well, to do that, we take the mass of each element, divide it by its molar mass. That's done for carbon, hydrogen, and oxygen. And from that, we get 4.05 moles of carbon, 8.11 moles of hydrogen, and 2.70 moles of oxygen. What we now want to do is turn those mole numbers into a ratio, a whole number ratio. The easiest way to do that is to divide each of the mole numbers that you get at this point by the smallest mole number, whichever of those values is the smallest. And in this case, it's oxygen, whose mole number is the smallest. The sample problem shows all three being divided by the oxygen's mole number at once. I'd be inclined to break this up into 3 separate division problems, and you'll see how I do this on my whiteboard in a moment. But when we do this, divide carbon's mole number, hydrogens and oxygens by oxygens, the smallest, we find that the ratio is 1.5 to 3 to 1. Sometimes at this point you will not get whole numbers, and in this case we didn't. When that happens, you need to multiply that ratio by the smallest whole number possible that gives you integers. And in this case it's a 2. We have to double all of these to turn 1.5, 3, and 1 into 3, 6, and 2. And we can see that depicted here at the bottom. All the numbers are being doubled to get the smallest whole number ratio of atoms to one another in the compound. The empirical formula for this one is C3H6O2. So we're going to scroll down, and I'm going to suggest that you do practice problem 2 on your own. Pause the video at this point if you're going to do so, and then come back when you're done and compare your solution to mine. So here's the solution to practice problem 2 on this on the same page, 147. All right, so I've converted immediately the percent compositions into masses. 9.93% became grams, grams, grams. Taken the mass of each element, divided them by their molar masses, and from that I get the moles of each element. 0.8268 moles of carbon, 1.653 moles chlorine, 1.653 moles fluorine. Sig figs on these don't matter so much because our goal is just to get the smallest whole number ratio. I divided each of those numbers by the smallest mole number, which was 0.8268 in this case. And when I did that, 0.8268 divided by itself is of course 1, and then these latter two values divided by 0.8268 are both 2's. If you're able to do that in your head, you're welcome to not show the division, but I recommend it in case you make a mistake. So there's 1 carbon for every 2 chlorines for every 2 fluorines, and that translates to a formula of CCl2F2. Carbon coming first typically in the formula of an organic molecule. So I've flipped my page, 148 of the ebook, 140 of the textbook, and we'll go up to this statement here. A compound's molecular formula, and that's what we're about to do, is to figure out how to solve for or determine the molecular formula of a compound, is an integral multiple of its empirical formula. Like earlier, when we were looking at that quick check, we saw when you go from a molecular formula to an empirical formula, you're dividing by the largest number into which all those go. Well, if you go the other way, we just need to figure out what to multiply that empirical formula by. How many times bigger is the molecular formula than the empirical formula? Down below it shows us how to do that, what the equation is to do that. Well, the molecular formula will be the empirical formula multiplied by this ratio, which is easily found, or most easily found, by comparing the compound's molar mass to the molar mass of the empirical formula. So in a molecular formula problem, where you're finding a molecular formula, you'll first typically find the empirical formula, and often it'll ask you to do that, but if it doesn't, assume that's a step you have to take. You then find the molar mass of the empirical formula, like we find molar masses typically, and then you'll be given the compound's molar mass in a problem like this. This will always be given to you, this value here, from which you can ultimately find the molecular formula. So we'll go down to the sample problem, look at how it's solved, and do the same thing again. Give you a chance to solve one on your own and compare your solution to mine. So the first step is to find the molar mass of the empirical formula, assuming you already have it. And if you don't, you'd find that first, like we just learned how to. That's just like a regular molar mass. You multiply the molar mass of each atom by the number of atoms in the molecule. There's only 1 carbon atom, so 1 times 12 is 12. 2 hydrogen atoms times its molar mass added up. And in this case, the molar mass of CH2 is 14 grams per mole. The next step is to divide the molar mass of the molecule that will always be given to you in the problem, in this case it's 42 grams per mole, by the molar mass of the empirical formula that in this case we just found. 42 divided by 14 is 3 in this case. What that's telling us is that the molecular formula has 3 times as many atoms in it as does the empirical formula, or is 3 times as massive. So we then multiply the subscripts from the empirical formula by 3, or we distribute 3 into each of the subscripts. So when we do that, 1 carbon and 2 hydrogens becomes 3 carbons and 6 hydrogens. And there is the molecular formula for this compound. So I flip my page, I'm on 149 of the ebook, and I recommend that you solve practice problem 1 on your own. Pause the video at this point if you're going to do so, and come back when you're done and compare your answer to mine. All right, so let's take a peek at what I got on my whiteboard. I just spent a couple minutes turning on and off lights in my basement to try to get the glare to go away. Still didn't work out. Anyways, step 1, remember, is to find the molar mass of the empirical formula, assuming you're given it in the problem, which we were. Again, sometimes you'll be asked to find that first. Or you'll be given the percent composition, and they'll say find the molecular formula, and you know that you've got to find the empirical formula along the way. So 1 carbon, 2 hydrogens, and 1 oxygen weighs 30.03 grams per mole. We're given the molecular formula's molar mass. So we divide the molecular formula mass, MFM, by the empirical formula mass and get 2. We then distribute that factor of 2 into the empirical formula. And when we distribute the 2 into CH2O, we get C2H4O2. Not that any of this is easy, but this is about as straightforward as a molecular formula problem gets. So you might consider trying another one of these practice problems to get it down and to see one that's just a little bit trickier. That is it, folks. Thanks for hanging in there with me once again. Lecture 7 is over, and it's pouring down rain outside on this Wednesday, September 23rd, 2020. See you soon.